Okay, so in this recording, we're going to look at more of the inner product between vectors and actually just do some concrete computation just to get a little bit more familiar with how these things go. So again, let's recall, like, so maybe let A and B be in vectors. And we have that the inner product is, there's two ways to define it, A times B, which is equal to the sum of A times BI, AI times BI, where I is equal to 1 to N. But then it's also the case that this is equal to the norm of A times the norm of B times cosine of the angle between the two vectors. Where that's A, that's B, and that's theta. That's like a quick rundown of the inner product formula. So now let's draw a bunch of vectors and see what happens. So suppose like 4, 5, 6, 7, 1, 2, 4. Okay. Let's make A like maybe A can be maybe like there. So this is -2, -2. That's A. And then maybe B can be 3, 1. And then maybe we'll have like C equals to -1, 2. This can be our C vector. Okay, so let's look at the corresponding products of combinations of these things. So for example, A product B. So that's going to be 2 times 3, 1. So this is what? -6 minus 2, right? So 6, 7, 8, so -8. And we see that that's less than 0.
Sorry, would A be -2, -2, or 2, -2?
Oh, good call. I was too busy trying to see if I could squeeze it over here. Right, like thinking about squeezing it over here, but I actually wrote it over here. So now this is going to be 6. So what is that? 2 times 3, 6, minus 2, so 4. And that is greater than 0, which I was about to have a very big problem with what we got because it was less than 0. And this is the angle between them, right? And I know that so thinking back to pre-calculus, so this is 0, this is pi over 2, and then here's pi. So if theta, so if we draw up a unit circle, right, for right? So any point on this unit circle is given by cosine theta, sine theta, just so you remember that. So any point on here where that's the angle, theta, right? So notice that the x coordinates on part of the circle over here between 0 and pi over 2, the x coordinates are going to be positive, right? So for theta greater than or equal to 0, well, I'll just say greater than 0, or greater than or equal to 0, less than pi over 2, implies that cosine of theta must be positive, right? Because anything on any point on this circle over here has a positive x coordinate. However, if we went over here, right, if we stretched all the way around, then this would have a negative x coordinate. So if theta, so pi over 2 is less than theta, which is less than pi, all the way around, or 180 degrees, then cosine has to be negative. So I had a negative right there, and I knew something was off because I know more or less that the angle between these two is going to be less than 90 degrees, right? So that's when you had a great timing for your correction, so I didn't have to figure out what went wrong. So now, for example, now if I look at the dot product of C, or the inner product of C and A, that should be less than 0, because the angle, the shortest angle between them is going to be greater than 90 degrees. So let's just like verify that. So C times A, so that's -1, 2, times 2, -2. This will be -2 minus 4 equals -6, which is indeed less than 0. So we see that angle, the shortest angle between A and C. It's definitely larger than 90 degrees, which makes me happy that this is less than 0. Oh, you're probably wondering why the dot product has anything to do with that. It's because of this formula here. This is always positive, so the norm of A is always greater than or equal to 0. The norm of B is always greater than or equal to 0. So the only thing that could possibly be negative in this product, for the inner product, the only thing that could possibly be negative is that. And that's only negative when the angle is between pi over 2 and pi. When it's bigger than that. When it's less than pi over 2, it's going to be positive, which means that this product is going to be, this is the only thing that can make it negative, which depends on the angle. So that's why I'm getting like excited about this. And when we talk about a certain algorithm in a bit, you'll understand why I'm concerned about being positive or negative and not the actual numerical value. Okay, so the other thing that I wanted to show numerically was the normalization of a vector. So if we normalize B, we have B becomes B over the norm of B. So what is the norm of B? It's 3 squared, so this is the square root of 3 squared plus 1 squared. So that's a square root of 10. So let me do a different vector actually than B, because I don't want to approximate it with some square root business. Let me do a different one. Like maybe, let me look at Um, 4 and 5. So like 1, 2, 3, 4. 1, 2, 3, 4. So I'll do there. I'll call this one D, and that's going to be 3, 4, 5, 5, 4. Oh, is it 5, 4, 16? No, that's not what I want. Sorry, I'm trying to get perfect squares in my head right now. I should know this way faster than it's taking me way too long. It's 4. So 1, 2, 3, 4. 1, 2, 3. There, that one. 4, 3. And that's my vector D. All right, so let's normalize D. So then D becomes D divided by the norm of D. So then what's the norm of D? The norm of D is the square root of 3 squared plus 4 squared, or the square root of 9 plus 16. This becomes 5. So the norm is 5. So then 3/5, 4/5 is the new vector. So this is the normalized vector. So 4/5 is almost 1. So it's like maybe there. 3/5 is a little bit less than that. So it's like there. That vector right there, see that it lies on the same line as D? That's going to be D over the norm of D. And what's so special about the normalized vector? Let's look at the length of it. We'll call this like D prime or something. So if we look at the norm of D prime, it's the square root of 4 over 5 squared plus 3 over 5 squared. So what does this become? Square root of 16 over 25 plus 9 over 25. Did I do that right? So this becomes square root of so the 25 over 25, or just 1. So normalized vectors are in the same direction as the original vector, but have unit length. They have length 1. So normalized vectors have unit length. And are in the same direction as the original vector. Okay. So normalized vectors will be convenient to work with when we start talking about things called bases, but that's like definitely next week. There's no way we can get to that today. Understanding that the unit product can be written as this formula, which means that the sign of the output depends on the angle between the vectors. is important. And I think as far as like basic operations on a single vector and between two vectors, that concludes all of the basic operations we can think of. Normalization and understanding the angle between it, that's all we need to know. So now I can stop this recording, and in the next recording, we're going to actually talk about applying this notion to an algorithm.